The key to success in working ideal gas law problems is knowing where gases sit in the mole roadmap if you get in trouble. Otherwise, you'll have to memorize the law and how to use it. The ideal gas law addresses ideal gases. But what is an ideal gas? Well, an ideal gas is a gas that has the molecules have very little, if any, attraction for each other. Then their volume is very small so that they don't have a significant volume when compared to the fact that they fill their entire container. It's a gas that isn't going to have any problems fitting into the ideal gas law. And when is a gas most likely to behave in an ideal fashion? Well, it behaves in an ideal fashion when the pressure is low and the temperature is high. Because when the pressure is low and the temperature is high, gas molecules are not forced close together. Therefore, they do not interfere with each other, if you will, and cause deviations from the ideal gas law. It's actually a combination of Boyle's, Charles, Amundsen, and Avogadro's laws. Let's have a look at it. PV equals nRT. PV equals nRT. Puvnert, where P is pressure in atmospheres, V is volume, and we usually express the volume in liters. You can express the pressure in any units you want to, but you better watch out for what your constants are, because that is the thing that's going to dictate how these units should go. As a rule, we use pressure in atmospheres and volume in liters. N is moles, of course, that's the universal designation of moles. R is the universal gas constant, and the universal gas constant we're going to use here is 0.0821 liter atmospheres per mole Kelvin. And the temperature is, of course, in kelvins. Now here's a problem. Let's calculate the number of molecules of gas in 286 milliliters at 41 degrees Celsius and 726 torr. Now notice something. I didn't say anything about the identity of the gas. Why is that okay? That's okay because regardless of what the gas is, it pretty well obeys those ideal gas laws, particularly if the temperature is warm and the pressure is low. So let's start out by finding the moles of the gas. Well, PV equals nRT. N then is equal to PV over RT. But remember what we're using for our gas constant. So N is 726 torr, but we've got to have the pressure in atmospheres. And it's 760 torrs per atmosphere. All right, this will get us to our pressure in atmospheres. Now let's introduce volume. The volume needs to be in liters. And oh, look, I've got 286 milliliters. But surely you can convert in your head. Sure you can. 0.0286 liters. All right, let's go to R. R, and learn this, it's 0.0821 liter atmospheres per mole Kelvin. Just memorize it. And the temperature, we'll take 41 degrees Celsius, add it to 273, and you get 314 kelvins. Now work it out, and you get N is 0.016 moles, regardless of what the gas is. And is that a good way of expressing the number of molecules? Well, it is. But to find the number of molecules in an exact form, you need to take the 0.016 moles and multiply it by 6.022 times 10 to the 23rd molecules per mole. And you see moles cancel. And this comes out to be 6.4 times 10 to the 21st molecules. It's really not hard. You have to remember what your units need to be. And learn that 0.0821 liter atmospheres per mole Kelvin. Write it on a sheet of paper in big numbers. Put it up there big and be sure and put the units there and tape it to your mailbox. And every time you drive in and out of wherever it is you park or come in and out, or out the front door, you'll see that. And I guarantee you in 2 days you'll learn it and not forget it. And frankly, most of the neighbors will too. Brought to you courtesy of Chemistry Professor, offering complete chemistry courses on DVD. Join us at our website on the World Wide Web at chemistryprofessor.com.